Hello and welcome to this video on energy. Specifically, we're talking about the conservation of energy once again. Previously, when we did conservation of energy problems, it was always transferring directly from one form to another. There was very little multiple types of energy present at a single time, and the process was fairly straightforward. Today, we're going to take that a step farther and start talking about what happens when there is multiple forms of energy present at various spots. And to do this, we're going to talk about shooting projectiles again. We've done this before as projectile motion, but today we're going to take a look at it through the lens of energy. In this case, there's a spring coiled with a spring constant of 475 newtons per meter, and it's compressed 0.12 meters. It is shot off a table at an angle. We'll talk about that in a bit. And it goes arcing through the air. Now, before I go too in depth with how to solve them, what we're going to do is we're going to start by setting up the bar graphs. If you think you can do this on your own or would like to challenge yourself, feel free to pause here and then check your answers afterward, but I'm just going to keep going. So in the beginning, the energy present in the spring is EEL, and the energy present in the height above the table is EG. The reason I include E, EL, and EG here is because I want to use a closed system. We don't have the tools right now to discuss what would happen in an open system, which is what would happen if I left gravity out, but so right now we're going to try to keep it simple. After the ball is shot, from here, it'll go up to point 1. Now, at point 1, it's not standing still. That only works if you're going straight up and down, or more accurately, the y velocity would be 0, but the x velocity would still be there. So it would have some EK. How much, we're not exactly sure. But would it have gained EG because you're higher up? At point 2, the EG would be back to the same amount it had originally, which means that the leftover energy would now have to be EK. Because it is a closed system we're looking at, the energy can't increase or decrease, it can only change forms. So my total number of bars has to maintain as 5, in this case, 1, 2, 3, 4, 5, throughout the entire problem. Any point AM just has different amounts of the varying types. At point 3, which is the instant before it hits the ground, would all be EK. Again, we are assuming a closed system with negligible friction, which in this case would be the ball, the earth, and the spring. This is a correction from what I'm writing on screen, because the ball and the earth would not factor the work done by the spring or the energy stored in the spring. So from here, the setup and the solving isn't too different from what we had done previously. I could find how fast it's going at point 2 or point 3 fairly easy. Point 1 is a slightly more complicated problem, but 2 and 3 are easy enough. Let's take a look at solving for the velocity at point 2 here. In the beginning, at my initial point, my initial and final point, the types of energy I have are EEL and EG. So my E initial will equal my E final because it is a closed system. So my E initial would be my E elastic, which would be 1/2 kx squared, plus my EG, which would be mgh. And I can put little initials on each of these. And that'll equal my EK and my EG over here. 1/2 mv squared final for the EK plus mgh final for the EG. Now, because these are the same height, I know that these will cancel out. I'll leave the numbers in for right now so we can see them. The only thing we're missing is the mass of the ball. Then we could go forth and solve it. So let's go ahead and assume the mass of the ball at this point. I've been talking about tennis balls. I don't see any reason to stop. There we go. So from here, solving for the velocity isn't that hard. I have my k, I have my x, I have my mass, which I just plugged in. G is 9.8. My height is 0.9. It'll be the same in both spots, which means it will cancel out. But again, we're going to go through the math just so we can see that. And I have my mass, which means I can find my V. So from here, it's just solving. And there you have it, 4.42 meters per second. The process is still the same, it's just you have slightly more moving parts on either side. You could follow this process and find the kinetic energy of the ball at the bottom or even halfway down. Either way you wanted to do it, you could go through and solve this problem. As for the higher point here or the slightly more finicky points, that would require a little bit of extra steps that you can watch in another video. Anyways, thanks for watching. Have a good one.